Okay, so we've talked about contextuality, we've talked about hierarchies of contextuality, and finally quantifying contextuality using the contextual fraction. And we talked about the contextual fraction as a monotone, as a resource monotone. And so this week's or today's lecture is sort of centered around the question of as a resource, but as a resource for what exactly? So we'll see that we are talking about as a resource for, and I will shorten it, measurement-based quantum computing. So, and we'll see roughly what measurement-based quantum computing is. In a nutshell, we will not give the full flavor of MBQC. Suffice to say that it's a variety of computation that's based off of measurement outcomes. So the central sort of organizing question is, what is contextuality a resource for? And as this suggests, we have one answer to this, which is computation. Schematically, the idea is going to be something along the lines of perhaps you have some restricted resources. So suppose that you have some input to a computation. Suppose you want to compute what they call a boolean function z2 to the n to z2. Now suppose that this function f, suppose that the way that you compute this thing is by you have some auxiliary sort of computer which sort of allows you to just manage these input bits. And what I mean by that is just do some simple linear arithmetic. So say you have some input bit string x, and you modify it, or maybe rather, I believe that we call this I, and you use sort of a linear side processor, as we're going to end up calling it, and you modify it to maybe some new kind of bit string q, and then you give this thing, you give this input to a genuine non-classical resource. So this is just a linear side processor. It does linear mod 2 arithmetic, and then you give it access to some additional resources, and we will see that these resources are maybe quantum states with contextuality, or maybe a PR box, or other types of empirical models. We can think of these as essentially resources. And from there, if we give it access to some resource, perhaps quantum, let's just put this as R, it gives us maybe some outputs, O, and then we use again the linear side processor to give us a bit, output bit, O in Z2. And so what is the whole point of drawing this whole string of stuff? The idea is that if I had just cut out this resource, all I could do is do linear arithmetic, but as soon as I give access to this resource is going to turn out to have contextuality, or in fact, for the cases that we're considering, strong contextuality. And then all of a sudden, the kinds of functions that you can actually compute are going to be, so the types of functions you can compute will be more expressive. So instead of just linear functions, you'll be able to compute nonlinear functions. So when we ask what is contextually a resource for, we say it's a resource for computation in the sense that given access to just some limited classical side processing computational power, the access to strongly contextual resources bumps us up to computing nonlinear functions, of which something like the OR gate or AND gate are examples of this. And from just, briefly, we sort of have an intuitive idea. Many physicists who haven't studied computer science, we get the idea, though, that you can sort of do any sort of classical computation using linear arithmetic, that is knots and maybe controlled knots, together with AND gates. And so AND gates would be computing a nonlinear function. So once I have access to these quantum, or rather strongly contextual resources, I will bump up the power of L, my linear side processor, to full universal classical computation. So we leave aside the question of precisely what somebody needs to do to arrive at universal quantum computation. So that's the purview of MBQC done proper. That is a system where if you have access to a linear side processor plus a quantum resource known as the cluster state, and you're able to do certain kinds of single qubit measurements, then this is universal for quantum computation. But that is sort of for another time, another place. I should say that this scheme that I've drawn here is a little bit simplified. So in the full, so in this case, I've basically taken an input bit string and then I've modified it to Q, which is the actual settings that I use to determine which measurements I do on my resource. So we'll make all of this explicit. And then I just do a single measurement to get some outcomes, like Alice and Bob each do. Q is going to determine which measurement Alice does, Bob does, Charlie does, so on and so forth. And then based on those measurement inputs, we get certain outputs. And then L will maybe add up those outputs so that we get like the parity of this output bit string. But the more general case, so when perhaps you have a more general sort of certain kinds of Boolean functions, you would benefit from actually having adaptivity. And so there the idea is you have some input to your computation, some input bit string, and L turns this into some, perhaps you use this to determine the first input to Alice, which tells us exactly, and then we give this access to a resource. So Alice measures her qubit on this quantum resource and gets an outcome consuming one of the qubits here. And then this, the output of this thing is sent again to, so maybe this schematic is not the best, but the output of this thing is then sent to the linear side processor. Okay, so maybe something more like this. The inputs determine at least the first measurement setting for Alice, who, given access to this resource, gets the first output, say O1, which is then fed in together with the original sort of I's and Q's to determine the next measurement setting, Q2. So there's some linear mod 2 arithmetic that goes for this. And then we, sort of iterate this for all the parties until we get some final output parity. Output is equal to sum, sum I, or rather k equals 1 to n of OK modulo 2. So we get this. Okay, so let's see an example. So luckily for us, there's plenty of examples to look at. So the first example is going to come from the PR box, which we've talked about before. The idea is going to be that I have some input bit string I1 and I2. I map this to some bit strings that tell me precisely, using L, which measurement settings I want to choose, Q1, Q2. So I'm deviating a little bit from some previous notation. Q1 and Q2 is consistent with for example, the paper of Robert Raussendorf, Contextuality as a resource for MBQC. So far it seems like L has not done much, but in principle, I1 need not be the same as Q1, I2 need not be the same as Q2, but Q1 and Q2 are linear functions of I1 and I2. It could be, for example, a constant function, but that would be not very interesting, because then we would only measure a single context, because Q is going to determine the contexts that are measured. Then, once we've determined the context to be measured, we give it access to a PR box, by which we mean we measure, Alice and Bob do a measurement on a resource, which is the empirical model of a PR box. We get some outcomes. So maybe I'll switch. Let's see what I was calling these. R1 and R2. Then I do again some linear side processing so that I compute R1 plus R2, which is the outcome of my computation. So I have a function that goes from I to, using the factoring through this PR box, the outcomes R1 plus R2 in essence. So how does this help us with computation? Let's get a little bit more specific. First, when we talk about I1 to I2 to Q1, Q2, we have some choices here. So this is in Z22. This is also in Z22. We could consider, for example, I1 going to, or rather, sorry, I should, the other way around, or rather I1 going to Q1 equals to I1, I2 going to Q2 equals to I2. This would just be a sort of very simple linear map, just completely linear. By the way, when I say linear here, I often mean affine linear for those people who are pedantic about such things. But we could have another example where I1 goes perhaps to Q1 equals to I1 plus 1, and I2 goes to Q2 equals I2 plus 1, or something like this. And any sort of linear combination of I1 and I2 plus constant terms would be completely fine. for our purposes, it will be nice to just be simple and use this particular map. I1 goes to Q1, I2 goes to Q2. And what do I mean by Q1 and Q2? More specifically, we say that when Q1 is equal to some bit j, then Alice measures xj. And when Q2 is equal to some k, that means that Bob measures yk. Hopefully that's still readable up there. So for simplicity, we are choosing this one in our example. Okay, good. Now, let's see, the empirical model for the PR box, if you recall, looks much like this. So we have Q1 equals 0, Q1 equals 1, Q2 equals 0, Q2 equals 1, and we have 1/2, 0, 0, 1/2, perfect correlations for the first 3 contexts, and perfect anti-correlation in the last one. Perfect correlation means that when Alice measures her part of the resource and gets 0, does her measurement and gets 0, then Bob must have gotten 0. And if Alice gets 1, then Bob must have gotten 1. And this is the same for this box as well as this one. But in the last box, we have that if Alice gets 0, then Bob always gets 1. And if Bob gets 1, Alice always gets 0. So these are anti-correlated. They always get the opposite. So how does the computation work? Roughly like this. So say we have the 0, 0 input I, then using this is going to lead to a particular Boolean function. When I choose I to map Q1 to be equal to I1, Q2 equals to I2. So we say that this is 0, 0 again. And then giving access to the PR box. So this is given L. What's going to happen? When I do 0, 0, Alice and Bob always get the same outcome. So they always get R and R, so that they're the same. And then the classical side processing always gives us R plus R equals 0. Now, you can sort of see that because of the perfect correlations, in the first 3 contexts, this one, and this one, we're always going to have the outputs be the same so that the final output or the outcomes of the measurements are going to be the same for Alice and Bob. Therefore, the output of the computation, rather, will always be 0. So 0, 1. We'll have 0, 1, 0. We'll have 0 again. And then if we do 1, 1, this time things are a little bit different. Maybe it pays to actually be a little bit more deliberate here. So if I have the 1, 1, then my input to the computation is 1 and 1, which means that I am measuring Q1 equals 1, Q2 equals 1. So this is the context that I'm looking at. the outcomes are always going to be r and r plus 1, so that they're always different, so that we have r plus 1 equals 1. Okay, so we can actually assemble this into a truth table. So we have something like, we have here the outcome of f, and then we have 0, 0, 0, 1, 1, 0, 1, 1, so that this is 0, 0, 0, 1. In other words, we have that f of I1, I2 is equal to I1 times I2. So that this is a nonlinear function. I would like to briefly just mention, perhaps without computing directly, that if you have access to a classical resource, what happens? Okay, so this is what happens when you have a PR box, which we've talked about as being strongly contextual. Suppose we had access to classical resources. So what do I mean by classical resources? Say I have a global outcome assignment. And what do I mean by that? I mean assigning to each measurement input, I assign a predetermined value. So I will just say that this is A0, A1 for the outcome of Q0, Q1 equals 0 and Q1 equals 1, and B0, B1. So what happens if I measure, so if I have the input 0, 0, then I get that this is 0 and 0 again, just mapping to Q's. Maybe I'll skip this step going forward. And then, so what does my resource tell me? So this is a deterministic or classical resource instead of a PR box. The outcome it's going to give me is precisely A0 and B0. A0, B0. And my linear side processor is going to tell me that the outcome of this is A0 plus B0. Similarly, if I do 0, 1, the outcomes of the measurements are going to be A0, B1. So I get A0, B1. We have A1, B0, A1 plus B0. And finally, 1, 1. This one will be A1 plus B1. So, for example, I mean, it's a little bit hard to see if you leave A0 and B0 just abstract like this, but you do see that they're just sums of numbers here. Okay, that doesn't tell us much. Suppose that we had that G equals to something like 0, 0, 0, 0, then you see that A0, B0 is just the constant function for all of this. So the function that you've computed for this particular one is precisely I1, I2 to 0, which is the constant function is affine linear. So suppose you had picked a different G is equal to 0, 1, 1, 0, for example. What's going to happen here? Here you're going to have f going to, well, you have 0, 0 going to 1. You have 0, 1 going to 0. 1, 0 going to 1, 0 is going to 0. And 1, 1 goes to 1. So let's see, what is this function? This is the constant function. This function here is, it looks like it's 1 plus, yeah, so I think it's something like f of I1, I2 is equal to 1 plus I1 plus I2. For example, I think that works. When these are 0, this is 1. When either of these are 1 and the other is 0, you get 0, 0. And when they're all 1, you get 1. Okay, perfect. And so this trend generalizes. The reason being, as we're going to see sort of later on in the more general case, the reason that this generalizes is because what you're essentially doing is taking each input, qi. So what am I doing when I define a deterministic or a global outcome assignment? I'm taking some qi, which is a input bit, and I'm mapping it to some, say, ai, or something like this, ci. And this is a map z2 to z2. Turns out the only way to write this map is precisely, the only kinds of maps allowed here are affine linear. So what you're essentially doing is defining from the input to the outputs, you have basically two affine linear functions that you're defining, or a set of them, which eventually leads you to having the functions that you compute just be affine linear themselves as well. The next thing that we're going to do is another example to sort of really get down the feel for what's happening here. As you might have noticed, the PR box is strongly contextual, and this allowed us to compute, instead of a affine linear function, boolean function, we got to compute a nonlinear one. So next, we've seen another example of a strongly contextual empirical model. And that is precisely coming from the GHZ empirical model that we've talked about. And that is also strongly contextual. And so there's an example due to Anders and Brown, which shows that the GHZ quantum state as a resource allows us to deterministically compute a nonlinear Boolean function, again, which suggests a bit of a trend where strong contextuality leads us to being able to deterministically compute nonlinear Boolean functions. So, as I mentioned, this example is due originally to Anders and Brown. So the idea will be very similar with a slight tweak, because the GHZ state, quantum state, is a tripartite state. So when we define, so we give an input, I1, I2, and we map that using linear operations to Q1, Q2, Q3, in which we have that, let's see, So I will just write this here. Q1 equals to I1, Q2 equals to I2, and Q3 is equal to I1 plus I2. Now we give access to the GHZ state and a certain, so these input settings or measurement settings are going to correspond to the Pauli X and Y measurements. So given access to GHZ measuring certain Pauli X and Y, we get some outcomes, R1, R2, R3, corresponding to each of the parties. And we use the linear side processor to compute the parity of this, R1, R2, R3. And it turns out to be the case, perhaps you guys remember, that the parity of these outputs from measurement outcomes from the GHZ state are very regular in that depending on the inputs, you either get that the parity is deterministically 0 or 1, and that's going to lead to a very similar situation with the PR box, where you deterministically compute a nonlinear Boolean function. So here, suppose we have, for some k, we say that if qk is equal to 0, this implies that we measure, maybe it's better to say it like this, we measure, so k is the party, so if qk is equal to 0, then xk is measured, Pauli x is measured on the kth qubit, and if qk equals to 1, then Pauli y is measured on the kth qubit for k equals 1, 2, 3. And this rule here guarantees that the contexts are of a very particular form. So if I have I1, I2 equals to say 0, 0, then this gives me 0, 0, or rather it maps to 0, 0, 0 in terms of q's, which is going to correspond to measuring x1, x2, x3. So going forward, we have that 0, 1 gives me 0, 1, and then 1. So this is x1, y2, y3, etc. And so you can see how this goes. If I do 1, 0, then it will be y1, x2, y3. When it's 1, 1, it will be y1, y2, x3. So I won't enumerate all of them, but we see how that's working. Perhaps, is there some benefit in writing this here? Let's save ourselves some room. Okay, so now we want to compute, I will just do this. What is P of R1, R2, R3, the outcomes of each of the measurements when I have the inputs I1 and I2? The way that I compute these probabilities is precisely through this expectation value, GHZ pi A1 R1 pi A2 R2 tensor pi A3 R3 GHZ, where this formula is the projector onto the plus or minus 1 eigenstate of the Pauli AI operator. So where PAR is equal to 1/2 identity plus -1 to the r a, where a is a non-zero Pauli operator. In this case, it suffices to just think of these as being x or y. The empirical model is something like this. Let's see if I can make this look okay. So the input 0, 0, 0, 1, 1, 0, 1, 1. And then we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1. So I have 1/4. So for the 0, 0 input, I measure the all x's, and the parity of the bit string is always 0. And when it's odd, the probability is 0. So this is 0, 0, 0. This one is 0. The others are 1/4, 1/4, 1/4. Also, for the rest of them, when you have an x and two y's, the parity of the bit strings that occur are always odd. So this one is 0. This one is 0, 0, 0. So, and then 1/4, 1/4, 1/4, 1/4. And so the others are exactly like this. By exactly like this, I mean like the second row. They have a possibility. The events that occur are only the odd parity outcomes. So in terms of the function that's being computed, you have a function f which takes 0, 0 and maps it to only the even parity bit strings that occur. So you always get that the parity of the outcomes is 0, so it goes to 0. 0, 1 goes to 1. 1, 0 goes to 1. 1, 1 goes to 1. And this function is precisely I1, I2 is equal to a little bit I1 plus 1 times I2 plus 1 plus 1, which when you expand it, this is again so the trend continues. So GHZ is a strongly contextual empirical model. We proved this previously. The way to show the strong contextuality of this empirical model is through a parity argument. Basically, we assigned, if you recall, assigned predetermined values to each of the measurements x1, x2, x3, y1, y2, y3, and showed that there is no consistent such value assignment. So we have here an empirical model that's strongly contextual, and we've computed a nonlinear Boolean function, and we have whether the following question of whether there's a correspondence between contextuality and computing Boolean functions. To give away the plot line, the answer is in the affirmative. So we will try to do a little bit in the way of showing the general case. So let's do a bit of a primer on measurement-based quantum computing. So a couple of things to just sort of recognize about MBQC, as it's sometimes called, is that the computation is driven as the name suggests, driven by measurements. So what do we know about measurements in quantum theory? We know that measurements are random. So what does that mean for our computational scheme? It means that, well, in particular, sometimes we want to deterministically compute something. So in the general MBQC setting, you actually want to be able to deterministically implement a unitary. So we won't get into that sort of perspective on MBQC. But there there's a particular unitary that you would have liked to implement in the circuit model. And the way you do it in MBQC is you set up this entangled resource state, and then you do certain single qubit measurements that, but you have to, because the outcomes are random, if you want to always implement the same unitary at the end of the computation, the randomness of the measurements ends up meaning that this implies that you need to have adaptivity for deterministic computation. In the general case. So we actually just looked at two examples where that wasn't the case. There was no adaptivity that we talked about in the PR box or the GHZ scenario. But in general, that will be the case. And so adaptivity of what? The idea will be that based on the outcome of Alice's measurement, Bob might need to switch which of the settings he was supposed to use according to Alice's input. So the version of MBQC that we will be looking at is an L2 MBQC is with it's a MBQC with mod 2 linear side processing. And so schematically, that might look something like you have some input, then you determine the input settings using L, and you have this more general sort of schema where maybe you do the first measurement on the resource state, you get the first outcome, and then based on this and some linear side processing, this determines the second input. Maybe this would be more appropriate. The second input, you do this into the second measurement and on the resource state, and you get outcome 2, so on and so forth. Okay. We can go a little bit further with the definition. The reason it's called L2 MBQC is because of the mod 2 linear side processing. So let us further say that we have an input to the computation I and an output. Given each I, we have an output O of I to the computation. Okay, so say we have n parties, then maybe I is a bad choice there. We have for each k equals 1 to n, there's a binary choice of measurement. We have each qk is in 0, 1. Okay, 2. For each k and each qk, the measurement outcome is also binary. K and qk, we have that the outcome sk is also binary. 3, we have that the output is the bitwise parity. So output of the computation is bitwise parity. So if the set of outcomes is S vector S1 to Sn, then the output of the computation is O of I, where I is the input, is equal to Zs, which is S1 plus Sn modulo 2. Arithmetic. 4, we have that, let's see, is there something? Okay, let's just have this full board be for the definition of MBQC. So we further have step 4, which is that the measurement basis is determined by the following linear equation. Q is equal to a matrix T, linear map T times S, plus Q, another linear map, times I. And this is in Z2 to the n, because this is determining for each party which ends. Okay, so as it is, this looks very problematic because the left-hand side looks like something that's an input, and the right-hand side seems to depend on outputs. So you need condition 5, which is that T is strictly lower triangular. This is for the purposes of causality. So if T is strictly lower triangular, what is that going to mean? So if I have T is equal to something that's of this form, say that this is the diagonal, and it's only here, well, what that's going to mean is that the first income, the first measurement input is not going to be determined, because of the strict condition, it's not going to depend on S1 at all. And so as you go on, you can have any sort of linear map between the previous measurement outcomes determining the current one, but you will never have the current or future measurement outcomes determining the current one. So causality is respected by using this lower triangular matrix. So now we want to catch the connection to computational power and contextuality. And to do this, we want to tie this L2 MBQC to a contextuality scenario, namely a Bell scenario. So if I have a contextuality or a Bell scenario where each party has 2 measurement inputs and each measurement has 2 outputs, this is sort of a well-known kind of this situation can be embedded in a certain kind of Bell scenario that's called N22 And so once we've connected our computational setup to a measurement scenario, we can at least identify something like what it means for, we can identify the notion of a global outcome assignment, and then we can also further define, because of that, we know what it means to be non-contextual, and therefore we also know what it means to be strongly contextual. So I mean, the sort of long and short of it is that an L2 MBQC is morally like an N22 Bell scenario, at least on the operational level of each party having access to two measurements, and each of those measurements having two outcomes. So this is the number of parties, number of measurements per party, number of outcomes per measurement. A little bit of a subtlety. The idea is, so if we have a contextuality scenario or measurement scenario, we need to define a few things. First is the set of measurements. So this is going to be defined in a particular way by you have a map mu going from z to n to x. So x is, so we're defining x sort of implicitly. I have the set of input strings, and I have a map to x, so that qk, which is a computational input, determines some mu of qk, which is an actual measurement in my set. So I don't necessarily want to exactly define the bit strings as labeling my measurements. Well, they do label the measurements, but they're not the elements of this set. And in particular, I want to think of these as being actual quantum observables. Next, we have the set of context. The set of outcomes is sort of clear from context. It will just be 0, 1 outcomes. So what are the contexts that are available to me? Okay, so maybe better to do it like this. We have a context is parameterized by an input setting q, which is equal to mu of q, k, sorry, a little bit quick with that, qk for k equals 1 to n. So the contexts in my measurement scenario are precisely given by those local observables, one for each party, which arise as the input. Sorry, is this? This is a particular bit in this bit string, and I'm mapping each bit in this string to a particular observable. Sorry, that's a little bit confusing the way I wrote it. In fact, wrong, to be honest, but I think you guys get the idea. We're considering the individual observables. So this will be in our set of contexts. One point of subtlety here is that the Q's may not be all possible bit strings. By which I mean we have a particular formula for how we get the Q's. The Q's are determined by this. And we want to do a particular computation, and for a particular computation, there's a linear map Q and a linear map T, which is appropriate for deterministically computing that function. Now, it could be the case that for a particular situation, that the Qs that you obtain are not all possible bit strings. And so it should be noted that this is why I sort of put this as a squiggly line. It's sort of morally like an N22 Bell scenario, but the set of contexts are not in bijective correspondence with all possible bit strings on n elements, n-length bit strings. We will use sort of like an embedding of this L2 MBQC inside of N22 momentarily, but I don't think too much is lost if you sort of see these things as synonymous for many purposes in terms of interpreting the results. And perhaps it's worth saying, maybe I'll put it here, that as a remark, we regard L2 MBQC, which we denote M, and L2 MBQC M as an empirical model. Which we write as E of M is equal to P of C of Q over all Qs. So what is the main theorem here? The main theorem is let M be an L2 MBQC that deterministically computes a nonlinear boolean function f goes from I to, let's just say a linear Boolean function f, then EM is strongly contextual. Okay, so let's think briefly about how to sketch the proof. The idea is going to be first that we assume that EM is not strongly contextual. So it's not strongly contextual, which means, if you remember the definition of strongly contextual, it means that there is no global outcome assignment in the support of this empirical model. So if it's not strongly contextual, then that means that we have G in O of X such that P of C of Q of the global outcome assignment restricted to C of Q is greater than 0 for every Q. So I'm just restating kind of what it means for this thing to not be strongly contextual, which is what we're assuming. And we're going to show that there exists a contradiction. So the idea is going to be the following. I mean, the main crux of the idea, which I'll say, is that we have an outcome for, given a particular sort of Q, let's leave aside adaptivity for a second. for a particular Q, okay, so say for the kth party, maybe this is a little bit better. For QK, what we have is that, or for the kth party, what we have is that we're assigning this a predetermined value, which is going to be precisely some outcome G of QK, which is also in 0, 1. So this is some input, which is 0, 1, and the output is 0, 1. So what you have is that the outcomes themselves, which we'll write as SK, is a map from Z2 to Z2. I mean, there's 2 inputs, 2 outputs. The only way to sort of really write something like this, you want to say that it's something that's affine linear. And in general, that's sort of the case. The one thing to be a little bit shaky about is we said that not all Qs might be possible because of the particular form of the computation. So it's true that a function of this form is affine linear. A little subtlety in the proof that took me a little bit to appreciate is that I can only write this down if both the inputs qk equals 0 and qk equal 1 occur. So one of the proof techniques that are used by Raussendorf in his paper is to say that first, let's embed our measurement scenario inside of N22, and inside of N22, all possible inputs do occur by just definition. So then within this extended scenario that encompasses the L2 MBQC, we can define these local outcomes as maps that are Z2 to Z2, and they're affine linear. So, and then later, once we've done all this, we can sort of restrict to the case, once we've defined all of this, it's completely trivial to just say that, you know, some of these inputs don't happen. So we can always restrict to the L2 MBQC case. And so if you have SK, which is affine linear, it means precisely that SK is equal to some CK plus DK times QK. That's what it means to be affine linear. So that in the general case, S is equal to C plus C is some bit string vector, D is some diagonal matrix times Q. So how do we proceed from here? We have an expression here for S, basically the fact that we can write these outcomes. When we have something that's a global outcome assignment, we have that for each input, we have a certain output, 0, 1 to 0, 1. In terms of N22, this is affine linear. Therefore, all of my outcomes can be written like this. And we have an expression like this for the set of outcomes, something that's linear. Oops. The punchline is essentially that we have another expression for S, which is precisely we have S is also inside of here, and Q is also inside of here. So we have a sort of self-consistency condition, which is that the S's, we can solve for S in 2 ways. S of Q, so S as a function of Q is equal to C plus DQ. But then we also have that we also have that Q is equal to TS plus QI. So putting these two things together, we get the identity plus dt s is equal to C plus dqi. And it turns out that this matrix is in fact invertible, so that we can write this as S is equal to, yeah, so this is diagonal, this is strictly lower triangular, so I plus this thing is going to have determinant 1, and over Z2, that suffices to show that this is invertible. So this is not a fact I was familiar with before this paper. And what this leads to is I plus dt inverse C plus dqi. All of this to show the following. This is a linear map, right? So because this is invertible, this is just some linear map acting on linear C, just an offset. And then this is also linear acting on the input. So you have that S of I is equal to some linear map K times I plus maybe some C prime. So this thing is linear. And so how does the proof go? The proof goes essentially that we assumed that, if you recall, M is an L2 MBQC that deterministically computes a nonlinear Boolean function f. Then EM is strongly contextual. Assume that it's not strongly contextual. There exists a global outcome assignment. After a little bit of subtlety, we show that by embedding it in a larger scenario, we have this linear expression, which implies precisely this linear expression for S, which is also, which I already said is affine linear, which is to say that we are not given, if it's not strongly contextual, then there's certain times with some probability we will not compute a nonlinear function but a linear function. So we cannot possibly deterministically compute a nonlinear function. And so this assumption must be wrong, and therefore EM must be strongly contextual. So the proof works precisely like this in the general case and with adaptivity. A couple of comments about this is that, so the result is proved by negation. And second, if you try to do something like this for qubits, the argument does not work exactly. There's a couple of subtleties. One is that if I want to define, essentially one of the key cruxes of this proof is that if something's not strongly contextual, I can think of a global outcome assignment as giving a map for each local party from their input to their outputs. Now, if you have outcomes that are not in Z2 and also inputs that are not, well, if say the inputs are in Z2, but the outputs could be, let's see, LD MBQC has D inputs and D outputs, I think. Hopefully I'm okay with that, but the upshot is that the corresponding function in an LD MBQC is not linear. So this exact statement needs to be modified. It will depend on D, and the degree of the function that you can compute with strongly contextual will depend on the D that you choose. But also in the case where you have qubits or D outcomes instead of two outcomes, this adaptivity part is not straightforward. So you have to restrict to t being 0, and you have a non-adaptive MBQC, and then you can make some statements. If I'm not mistaken, but I have to check, maybe one of the things is that you're no longer guaranteed that this is invertible, perhaps? I have to check, but the same argument does not go through, even after modifying the statement a little bit from being nonlinear to a Boolean function of certain degree, or a function of certain degree, rather. Okay, so I think that concludes our discussion of strong contextuality and hierarchies of contextuality. The next lecture will be about state-independent contextuality, which is sort of like, the strongest possible contextuality that you can have. Roughly, maybe you can't, on a sort of moral level, high level, you can't really define something like this, G as a global outcome assignment, when you have a sufficiently rich set of observables, quantum observables, satisfying a certain algebra. If you have this situation, then you can't even define an outcome for each of the measurements in your set. So you can't even define what it means to have a non-contextual model, empirical model, and therefore, ergo, you can't really define these non-contextual polytopes. You can't define anything the way that we have, because you can't even get started with defining what it means to be non-contextual in some sense.